This is the well-known display of the magnetic field of a permanent magnet displayed by the distribution of iron filings. The whole of this program is about displaying magnetic fields in one way or another. But of course the trouble with magnetic fields is that you can't actually see them. So what I've got to try and do in this program is demonstrate them to you and show you that they can be shaped and controlled by showing their effects rather than the fields themselves. This particular display of the magnetic field of a permanent magnet shows the field very clearly because the iron filings distribute themselves along the directions of the lines of force. If that's a north pole and that's a south pole, the lines of force run from the north pole to the south pole, and the iron filings distribute themselves along these lines, pointing towards the pole pieces of the magnet. So in that particular instance, the field is very clearly demonstrated. I can represent this with a diagram. Here, there's a diagram of a permanent magnet, north at one end, south at the other, and the lines of force are running from the north pole to the south pole, roughly along the same patterns as you saw in the iron filing demonstration. So this is a simple graphical representation of the kind of thing that happens with a permanent magnet. Now let's put two permanent magnets side by side. This is the distribution of lines of force that you get. They're squeezed together between these two magnets when the north is next to north and south is next to south. What does that actually mean in practice? I can show you this with some actual permanent magnets that I have here. They're permanent magnets made of steel, the north pole marked at each end, so that this resembles the diagram that you've just looked at. If I push the two together, quite clearly one is repelling the other. If I press the two together side by side, it's firmly pushed away. So there's a force of repulsion here. So let's look back at the diagram to see how that might explain it. You see here the lines are apparently compressed, and they actually behave very much as though they are elastic and compressible, so that when lines of force get compressed like that, they do represent a force of repulsion shown here by these white arrows. If I turn the magnets round so that north is now facing south, I'm sure you're very familiar with the fact that they attract one another like this. This again can be shown on a diagram. Here the lines of force now running from north to south are, so to speak, pulling the magnets together, and there's a force of attraction, as again shown by the arrows. That much, I'm sure, is very familiar to you. The first main point I want to get over is that actually these fields can be quite easily shaped by using pieces of iron to do this. Here I've got some pieces of iron. They're not magnetic at all. They don't attract each other. But if I put them alongside these magnets, like this, along one side, so that the two magnets face each other once again, the two north poles repelling, two north poles opposite each other, so that the magnets should repel each other, what do you think will happen? Let's see. Nothing at all. The force of repulsion has been almost completely removed. So what's happened is that the magnetic field which was filling this gap between the magnets has been shunted away down the iron. Iron is a very much more attractive route, provides a very much more attractive route for magnetic fields than does air. So it shunts it away, and the force of repulsion is removed. Let's have a look at this in a diagram. Here you see the magnetic lines which were in the gap between them, as they are still outside the gap. But now the lines have been shunted through the iron, represented by this light grey area, shunted through there, lines again running from north to south on both magnets, and the gap between them, you see, has no lines of force left, so there's no force of repulsion left either. Now I can demonstrate this effect rather more dramatically with a different pair of magnets. Here I have a ferrite magnet It's a magnetic material, ceramic in nature, and it can be magnetized quite strongly. Here you see there are two rings, one above the other. The upper one is being supported by the magnetic force exerted by the lower one, or the magnetic forces interact, to be more exact. This kind of levitation of a body due to magnetic field will be demonstrated in the next television program, where the method is used to levitate a train above the track. But I can show you how the field can be shunted away from these two by taking these pieces of iron again and slipping them between the magnets. As I put them in, the magnetic field is gradually removed until there isn't any left, and the upper magnet sinks down onto the lower one, and there's no force of repulsion left. Removing these pieces of iron restores the levitation of the ring magnet. So shunting a magnetic field is an important ability that you can use to shape the magnetic fields for practical purposes. A more important use is guiding a magnetic field from a permanent magnet to the place where you actually want it. I can demonstrate this quite easily. Here I take a permanent magnet, and of course it attracts one of these pieces of iron to it in the normal way. But now the other end has become a magnet. The north pole that was here has turned that into a south pole, this into a north pole, so now the magnet has been extended. The magnetic field has been transferred to a different place. If I remove the permanent magnet, the piece of iron drops off the far end, though putting the magnet back restores it. So guiding a magnetic field from where it's generated in a permanent magnet to where you want it is another important ability that we have. I can demonstrate this for a practical purpose, for practical purposes, by showing you how a magnetic field for a moving coil meter is generated. So let's return to the demonstration that we had of the permanent magnet using iron filings to see how this can be done. Well, first let me remove the iron filings from the bar magnet as they were, because I want to put some pole pieces onto this magnet to show how we can get the field where we want it. Here I've got two pieces of iron which are shaped like the pole pieces needed for a moving coil meter. Their shaping is arranged so that there's an air gap in there, and we put an iron armature so that the gap is now annular in shape. We have taken the magnetic field produced by the bar magnet which is there and guided it to this annular ring. Let's have a look to see what the field is like now. If I sprinkle iron filings over it, particularly in the gap we're interested in, but let's put some round the bar magnet as well. There's still a field down there, of course, but most of the field, as I think you can now see, is concentrated up in this annular air gap, and the lines of field seem to be radial. That's to say, it's directed from the center of the armature out to the circumference of the air gap, and so that the lines of force are always directed towards the center, and so that when there's a coil in this air gap, with the wires running down into the gap there, with the field in that radial direction, it's always at right angles to the coil, and so there will always be a force around the circumference of this annulus. And that's exactly the direction that's needed, because if there's a pointer attached to the coil, it'll be deflected like this and will move across the scale of a meter dial. So that's how one can direct magnetic fields to the point in a moving coil meter where you want it. So let's now go and look at a real moving coil meter. Right, over here we've got a couple of meters arranged so that they've got a current passing through them. One of them has its dial in the normal way, and you can see the meter deflected, showing a reading of about 300 milliamps. But the other meters had the dial removed so that we can see what's going on inside. At the top here, you've got the bar magnet, the permanent magnet, and on each side of it there are the pole pieces which take the magnetic field round to the annular air gap, which I was showing you in the previous demonstration. In the middle, you can see, if you look carefully, the iron armature, so that it generates this annular air gap. And if I move the pointer backwards and forwards, you can see the coil moving in the air gap, experiencing a force at right angles to it and causing the deflection of the pointer. I can vary the current in the meter and so vary the deflection in this way. There's one other thing I'd like you to look at, if you can see it. It's a tiny coil spring at the front here. That spring is there to ensure that the pointer reaches a particular deflection corresponding to a current. The force on the current is constant, independent of the deflection, but the force of the spring increases as the deflection increases, so that the pointer comes to rest at a point at which the force on the current is exactly balanced by the force produced by the spring. This then is one simple and straightforward use of iron pole pieces for the purpose of shaping a magnetic field. Now let's go and look at another application of this principle. Here's a loudspeaker. It's actually playing music. The loudspeaker's been removed from the sound box so that the quality of the sound isn't all that good. But nevertheless, this is a similar application of the principle of guiding magnetic fields to a particular point that we want it. And let's see how this is done. I've cut away another loudspeaker so that you can see more easily what's happening. At the moment, it's being driven by a sinusoidal waveform, and as you can see, the cone is vibrating in and out in response to the current supplied to it. If I vary the frequency of the current, you can see the cone vibrating more rapidly and more slowly. Now, if I turn it round just a little bit, I think you'll be able to see where the coil is and how it's interacting with the magnet. In there is the coil, and it's moving in and out of an annular air gap. And that air gap is in the magnet. Now what I want to show you is what that magnet is like when the pole pieces have been shaped so that they interact with this coil and produce this kind of movement. First, let me just show you what it's like when it goes up to higher frequencies. At a certain point you can hear it, and then as it goes down in frequency you can actually see it rather than just hear it. So let's have a look at a loudspeaker that's been broken open even further. With this loudspeaker, I can actually remove the cone completely and show you the coil in its entirety. As you see, it's attached to the base of the cone. But what I really want to look at is the magnet. To make it clear what's happening, I've taken a magnet from another loudspeaker and cut it in half. You can see how it's located in the back here. If I superimpose it on the picture of the loudspeaker that I've taken the cone away from, you can see where this half would be if it were in fact the loudspeaker magnet. But now let's have a look at the cross-section of the magnet. As you can see, there is a magnet which is made of ferrite, very similar to the magnets I was showing you early on. Next to the south pole, there is a flat disc, or washer-like disc with a hole in the middle. And that brings the south pole up to the outer edge of the annular air gap. The north pole, which is the other side of the ferrite ring, is connected to another disc, and there's a pillar at the center which brings the north pole up to the other side of the annular air gap, so that across this air gap there is a radial field from north to south all the way round. And the coil on the cone fits into that air gap like this and moves in and out as a current passes through it. So that's another example of how you can shape magnetic fields for practical purposes. Now that's all I want to say about shaping the magnetic fields due to permanent magnets. What I now want to show you is how you can shape the magnetic fields to produce useful devices using alternating magnetic fields generated by AC currents. Now here we've got the demonstration again using iron filings to show a magnetic field. There's a current flowing through this coil, and as you can see, there are lines of magnetic field threading through the coil showing the nature of the magnetic field. In this particular case, it's rather weak because you need a large current to produce a magnetic field when there's no iron about. But the big advantage of a magnetic field generated by a current is that you can reverse it. So if I switch over the direction of the current, you'll see the pointer is able to rotate and show a reverse direction of magnetic field. But this isn't the best way of exploring a magnetic field due to a current. Let's go over and see how this can be done much better. Over here, I've got another coil. This one has 500 turns on it, all insulated one from each other, and it's being driven by an alternating sinusoidal current. The voltage across the coil is shown on the lower trace here on the oscilloscope. Over here is a meter which is measuring the alternating current through the coil, but we'll come back to that in a moment. For the time being, I want you to pay attention to the voltage waveforms on the oscilloscope. But what I want to do is to show you how the field generated by this alternating current flowing through this coil can be observed by another coil. Because the current's varying, it means that the magnetic field generated by the current is also varying. But a varying magnetic field will generate a voltage in another conductor which is lying within the field. So if I bring up another coil, place it alongside the first, if there's any field there, then it'll be picking it up, generating an EMF, and you'll see on the upper trace the voltage which is being picked up by the secondary coil is now being shown. And if I move this coil around, you'll see that there's a stronger field when the two coils are one on top of each other. In other words, the field which is through the center of one coil passes or tends to pass through the field through the center of the other coil. Now, to explore the field properly, I ought to try to follow it round and explore the way the field gets bigger and bigger as I get close to it. As you can see, in order to do that, I have to turn the coil over. If I just lift it up and put it on top as I did in the first place, you can see the phase changes. At this point, the phase of the secondary waveform is changing, which shows that, in effect, the field is first going through it in one direction and then through it in the other. So that's how you can explore the field produced by one coil by the presence of another. But I'm sure you'll realize that what I'm actually showing you, or another interpretation of what I'm showing you, is the construction of a transformer. But this is a very inefficient transformer. Although the two traces on the oscilloscope screen are about the same size, that's only because the scale of the upper trace is very much more sensitive than the lower trace. And to make an efficient transformer, I'd need much better coupling between the magnetic field produced by the primary and that picked up by the secondary. Now, as I'm sure you know, one way of achieving this improvement is to couple the two coils by a ferromagnetic field or ferromagnetic path. So if I put the two coils on this iron core, look at the upper trace, which tells you the voltage on the secondary, and it increases. In fact, it goes right off the screen. So in order to observe this properly, I must change the scale on the oscilloscope so that the two waveforms are comparable. Now, I've increased the sensitivity of the upper trace by a factor of 100 or more, but still the output voltage from the secondary is not as big as the input voltage to the primary, even though both coils have the same number of turns. Both have got 500 turns. What I have to do is to complete the magnetic circuit with another piece of iron that completes the magnetic circuit now, so that the output voltage is almost exactly the same as the amplitude of the input voltage. Notice if I introduce an air gap, the output voltage drops quite quickly. Even small air gaps will destroy the quality of a good magnetic circuit. So that's how to make a simple one-to-one transformer, the output voltage being very nearly the same as the input voltage. Now, I hope you remember that the output voltage is equal to the input voltage only if the turns ratio is 1, same number of secondary turns as primary turns. Let's test this out by trying a secondary coil which has a different number of turns. I'll take this coil off of 500 turns and replace it with one of 1,000 turns. Transfer the leads so that the upper trace now displays the voltage on the secondary. Complete the magnetic circuit again, and you'll see we've got an output voltage now which is twice the input voltage. Again, an air gap reduces the output voltage very considerably. So that the main message I'm trying to get over at the moment is that to get a good transformer, you must have a very good magnetic circuit. Otherwise, flux will be lost. The flux generated by the primary won't reach the secondary. Now, breaking the magnetic circuit, as I'm doing here, doesn't just affect the output voltage, as you can see on the oscilloscope screen. It also affects the current going into the primary coil, as you can see on the meter. As I break the magnetic circuit, the current into the meter changes. I move the coil here, you can see it a little bit better. As I break the magnetic circuit, the current through the meter changes. Now, why does this happen? If the current is increasing, as it is when I break the magnetic circuit, this is because the impedance of the primary coil must be decreasing. Now, you may remember that the inductance of a coil is proportional to the number of turns squared, and that isn't altering as I change the magnetic circuit, divided by the reluctance. So, if the reluctance decreases, the inductance increases. And if the inductance increases, the current through it decreases. So that as I increase the reluctance, the inductance decreases and the current increases. As I decrease the reluctance, the current decreases too. So you can see the magnetic circuit is important for two purposes, for two reasons. Firstly, it ensures that the relationship between the input voltage and the output voltage is in fact equal to the turns ratio. And second, it ensures that the current drawn into the primary of the transformer is no more than it need be. Well, I hope this demonstration has made some of these points clearer to you than they were before.